lecture will be focused on fundamentals of quantum programming, first of all, but then we will discuss different quantum algorithms, basic quantum algorithms, but also we will discuss novel research results. And at the end, I have Jupyter notebooks, so I have examples of quantum programs, and I hope that it will be interesting and useful for all the presenters here. So the title is in the slide, and the outline is the following. First of all, we will discuss the basis of quantum programming, then we will discuss and we will try to understand all these, not all, but basic examples of quantum algorithms and what does it mean that we have quantum supremacy. Then we will consider different models of quantum systems, and also consider quantum protocols for studies, not just quantum systems, but classical systems and their properties with quantum computing. So the notion of quantum bit, and I will say not just quantum bit, but shortly qubit, is the following. So in comparison to that we have in classical programming, we operate with classical bits. In quantum computing, we act on the states of quantum bits. Quantum bit, it is a unit of information in quantum programming. And very interesting property of quantum bit is the following, that in the case of quantum system, we can achieve superposition of 0 and 1, the state 0 and 1, and this superposition can be prepared in different proportions. So in this slide, you can see these constants, C1 and C2. These constants are complex constants, and the basis states in quantum programming are states, eigenstates of sigma z operator, which are used, the notation for them 0 and 1, and we have these arrays or vectors, in other words. Very often, if you speak about quantum bit, and if you try to find some information about quantum bit, you will find this sphere. And why do we have such representation for quantum states of single qubit states with a sphere? Let us try to understand. Thank you. So as I told, these constants, C1 and C2, they are complex constants. So we can rewrite them in the following form. So we have the absolute value and we have this exponent, so we have this phase. And we have the same expression as was here, but rewritten in another way. Then, of course, we can rewrite these two terms and just from more convenient form, we rewrite these two terms in this form, and we know that the total phase in quantum state, so we can omit this product, so we can neglect with this total phase in quantum states and leave just these two terms. From the normalization conditions, these absolute values have to satisfy these conditions. So the sum of absolute values squared for these two constants has to be equal to 1. So minus one parameter from this condition. So we have just two parameters that can be used to describe arbitrary quantum state of one qubit. And it's very convenient to use the following representation. So instead of writing these constants here, absolute values of these constants, because these constants has to satisfy this condition, we write cosines and sines, and we know that the cosine squared plus sine squared we have in this simple expression, this simple expression equals to 1. So we have just two parameters, and these parameters can be considered as coordinates in spherical system of coordinates on this sphere. So each dot on this Bloch sphere, this sphere is known as Bloch sphere, represents different states of one qubit. So the state 0 is here, and the state 1 is here, and all superpositions are in different locations on this sphere. So the question is the following: how many states can we achieve just for one qubit? The answer is infinite. So infinite number of states, infinite number of superpositions we can achieve. This is in very similar to that situation if, for instance, we have two colors and we mix them and create another color. So how many different colors can be obtained? The answer is infinite numbers. Then, more complicated case. If we have not just single qubit quantum states, but we have 2, 3, 4, and more qubits in our systems. So let us first of all consider just 2 qubit case. In this situation, we can consider 4 different basis vectors. It is 0, 0, 1, 0, 0, 1. Sorry, this is some mistake of representation. And 1, 1. How can we find the matrices corresponding to these states? The rule is the following. We have to consider the direct product of these states. So we have not just multiply these vectors. We cannot do this according to the rules of mathematics. But we have to consider direct product. The rule is the following. We have to multiply each terms of the first matrix to the terms of the second one. And at the end, we obtain this vector, and the number of components in this vector is equal to 4. So we have 4-component vector, which represents the state 0, 0. In the case of state 1, 0, we have the following result. In the case of state 0, 1, we have the following result. So you can do all these calculations by yourself, because it's very simple to multiply 1 by 0, 1 by 1, 0 by 0, 0 by 1, and obtain all these vectors. And here, sorry for this, here it should be state 1, 1, and we obtain the following vector. And the question is the following. Can we represent arbitrary 4-component vector with all this, with the help of these terms? The answer is yes. So we have 1 in the first position in this case, 1 in the third position in this case, 1 in the second position in this case, and the last position here. So we can multiply these terms on the constants, arbitrary constants, and create arbitrary vector. I can't help me. if we consider not just one qubit case, but consider 2 and 3 and many qubits, we have also to say about another fascinating property, not just superposition, but entailment of quantum states. So let us consider the following situations. So we have two quantum systems, and we use the notation A and B for each of this system. And if we can rewrite the state of quantum system composed with components A and B as direct product, you know what does it mean, this direct product from here. The rule is the following. So you have the rule how to multiply these states. So if you can do this, the state is not entailment. If you cannot do this, the state is entailment. So let's try to understand in examples. So let us consider particular cases of quantum states. So let us consider the following state. The following state is superposition of two basis states. We have 0, 0 state and we have 0, 1 state. And we can rewrite this state in the following form. So we have clear understanding that the state of qubit 0 is 0 state, and the state of qubit 1 is superposition of 0 and 1 states. So we have clear understanding what do we have in our system. So the state is not entailment because we can rewrite this expression in the following form. And if we consider this case, we cannot do this. So we cannot understand clearly what do we have in such situation. In this term, the state of qubit 0 is 0, the state of qubit 1 is 0. In this term, the state of qubit 0 is 1 and the state of qubit 1 is 1. So we cannot find answer on the question, what do we have for each qubit? What state we have for each qubit? So the state is entailment. So let's try to solve some particular problems. I see some students in the online, so can you answer on the questions? So what do we have here? We have two examples for different states of two qubit system, and is this state entailment or not, or is this state entailment or not? Do you have students in chat? Maybe they can write some messages. Однакові. The both are наступний функцій. This is entailment state, and in the case of this state, we have the state is not entailment because we can find this expression here.
There is some
This is some sorry for
Some
misprint. Some misprint. Yes, this is sorry for this. So very sorry for this. So if this is the same state, is 0 here, and we will have entailment. Sorry. So in the case of two qubit state, we have superposition of 4 terms. In the case of n qubit states, we have 2 to the n superposition of 2 to the n terms in our quantum state. So this is fascinating amount. Let us also try to understand what do we have if we program with quantum programming and operate with quantum states. So we consider different gates. The simple case of quantum gate is the NOT gate. So the action is very simple. We act with not gate on 0 state, and we obtain 1 state. And the opposite situation we obtain in this case. In the case of controlled mode case, we have a more complicated situation because depending on the state of qubit 0, we have action on the qubit 1 or we do not have action on the qubit 1. So if the state of qubit 0 is 1, we have to change this state to the opposite. So the action of controlled NOT gate on the state 1, 0 is 1, 1, and the action of controlled NOT gate on the state 1, 1 is 1, 0. Similar case is in the case of 3-qubit gate. CC NOT gate controls twice controlled NOT gate is the following gate. So depending on the states of qubit 0 and qubit 1, we have action on this state or not. So if the state of qubit 0 and qubit 1 is 1, simultaneously, so we have 1 and 1 here, the action will be considered. So the action of the controlled NOT gate on this state is the following. So I use the color to show that we have changed these states. And the action of controlled NOT gate, for instance, in this state is just the same state. A very interesting case is Adamar gate. After action of Adamar gate on 0 state, we have superposition zeros and ones. After action of Adamar gate on 1 state, we have superposition also 0 and 1 state, but with different signs. So we have plus here and minus here. And also, very often, phase gate is used. The phase gate acts on state 0 and gives us the same result, but after action of the phase gate on the state 1, we have this product. We have exponent with parameter phi, which is used in this gate. In this example, you can see this parameter equals pi over 2. And very often we use in quantum programming to model quantum systems, spin systems with quantum computing. We use rotational gates. They are Rx, Ry, Rz gates, which means that we have rotation around X, Y, and Z axis. And the parameter theta is used here, and this is the angle of rotation of quantum state. And the explicit expression for this operator is the following. So we have exponent, and here exponent we have sigma x, sigma y, and sigma z operators. And these operators are Pauli matrices. So, and the notations are commonly used as the following. Also, recently IBM Quantum Composer and other platforms gives a possibility to directly to program with RXX, RYY, RZZ gates. What does it mean? That we have operator, and in exponent, in comparison to this case, we had just one sigma x, and here we have sigma x corresponding to 0 qubit because we have 0 index here, and sigma x corresponding to 1 qubit because we have 1 index here. So this is 2-qubit gate which acts on this state of qubit 0 and qubit 1. Then, very often, another gate which is used very often is swap gate. So if we would like to replace this states of 2 qubits, for instance, in this case, we can see very clearly that after action of this swap gate on this state 0, 1, we obtain 1, 0. And after action of this gate on this state 1, 0, we obtain 0, 1. So we have changing of these positions of these states, replacement. And because I didn't have answers from students, maybe I will skip these examples, just a few seconds explain that, for instance, in this case, after action of controlled NOT gate, and here it's very important to see what indexes we have. So we have 1 and 0. So what does it mean? That 1 qubit is controlled and 0 qubit is that qubit on the state of which the NOT operator has to act or not. So after action of this 2 qubit gate on this superposition, we have the following results. So if the second qubit is in the state 1, the state of first qubit has to be changed to opposite. So NOT operator acts on this state. So after action of controlled NOT operator on this state, we have 0, 1. And here we have just 0, 0. And here we have 1, 1. Because the second qubit is in the state 1. And another example, maybe students non-say names. So after action of this pop gate on this superposition, we obtain the following results. So this is the basis, very simple examples, just for understanding, because I understand that for clear understanding and maybe for better explaining of this material. Also with students and even with high school students, I practice with the following tasks. So if I have different quantum protocols, how to understand what do I achieve after action of all these gates. So here I have NOT gates and I have controlled NOT gate. And the first step is the following. After action of these NOT gates on the states of qubit 0 and qubit 1, and I have to say that at the beginning, the states of all qubits are prepared in the state 0, 0, 0, 0. So after action of these NOT gates, we obtain states 1 and state 1. And after action of this controlled NOT gate, because this qubit is in the state 1, this operator will act on this state qubit 1, and after action of NOT operator on this state 1, we achieve 0. So 1 and 0 state. In this case, because after action of these NOT gates, we obtain 1 and 1 state 1, 1, and then state 0. And this twice controlled NOT operator acts only in the case when all these qubits are in the state 1. So we have this situation. So the result of this protocol is the states 1, 1, and 1. So this is the result. And also other examples so students can practice on them, so can find very quickly answers. Why do we need this training? Because in quantum programming, very often we use expertise of knowing how to combine different gates, not just simple gates as in this case, to prepare some quantum states or to prepare some quantum oracles.
For instance, in the second scheme,
Yes,
this
one.
Yes, this one. We will have 0, 0.
We will have 1, 1 because this is the answer. Yes. This is already the answers.
Yes.
So at the beginning, this state is 0, 0. After action of NOT operator on the state 0, we have 1 state. And one state, this qubit is controlled qubit. So this operator acts on the qubit 1, which is in the state 0. And after this action, we obtain 1 and 1 states. So we have not this text here.
The one below, we have
This one?
zero. Oh, no,
This one?
this one, yes, we have zero because we have additional operator.
Yes. After action of this gate, we have, so considering two NOT gates is just identical operator, unit operator, identical state. So it's very, high school students like this examples, like this tasks very well, because they can understand, because we have just classical gates. We have just control, not gates, not complex numbers. We do not have here rotation. So I use these examples even if I have in the frame of junior Academy of Science practice with students, and high school students can do this. But this is not all the quantum programming. It is just the basis, very basis of this science. This is the science, but to explain and for the basis understanding, these examples are very nice. Maybe there are some other questions.
So this is operator, but typically it means this is some device.
Yes.
For each operator.
Yes, this is the symbolic representation. This is called, in quantum information science, this is called quantum protocol. This is called quantum protocol. This is visual representation of quantum program. But this is the most simple case, because we have just 2 qubits, and here we have C4. This is classical qubits, because they have to be used in order to write the information from quantum programming on some classical bits. So we have 4 classical bits here. So in the case of multi-qubit quantum protocols, we do not use this representation. We use just schematic even, because it's inconvenient to draw the lines for each. For instance, if we have 100 qubits, it's inconvenient to draw these lines and to consider action of all these gates. So we consider states, we consider programming with Python, and so on. So we consider programs in cycles and so on. But schematically, if the protocol is scalable, well scalable, we can, of course, use quantum protocols, such representation. So this is quantum preparation of quantum state on a quantum computer. What gates do we use in order to prepare, for instance, this state? Or what do we have as the result of action? So different types of questions. How to prepare these states, or if we have action of these gates, what do we obtain?
Can we imagine that this is not quantum system, but a classical system?
In this case, yes, because we have just classical operators. We have NOT, this is classical. We have control NOT, which is also classical. We have if operation. So if something is achieved, we obtain action on it. Can I move to the other slide? Okay, I hear my voice. It's okay. I cannot speak this slide. Can you help us? Sorry, this may be a problem with the tool. Okay. So there are different quantum algorithms already developed, and we can say that we have few directions of developing of quantum programming. First of all, I have to say that this is search algorithm, optimization algorithm, factorization, but also studies of quantum and classical systems with quantum programming, quantum machine learning, and many others. So I would like to explain just for students if they hear me. The most simple case of quantum algorithm, which is most simple for understanding what is doing here in this quantum state, but the most simple for explaining what we achieve at the end and what is the problem. So this is Bernstein-Vazirani algorithm. And the algorithm, the aim of this algorithm is to find a secret string, and the string is the numbers 0 or 1s, and we have different lengths of this string. And in the classical case, if we have question, for instance, we have string 0, 1, 0, 1, so we have 4 numbers in string. In classical case, if I ask, what do I have in my secrets? What numbers do I have in my secret string? I have to perform 4 manipulations. So I have asked this classical computer, what is the first number? What is the second number? What is the third number? And what is the fourth number? And I will obtain the answer. In quantum case, I have to do just perform just one manipulations, even if my string is of length 100, 1000, arbitrary lengths. Why do I have such type of algorithm? Because, of course, because of this superposition, and also because of the entailment, because here I create this entailment due to 2-qubit gates. So this is also the quantum protocol. This is quantum protocol which corresponds to this algorithm. And the encoded string here, unknown string, is 1, 1. So the structure of this protocol is the following. We have to prepare the initial state. Then we have to use this part, which is called quantum oracle. And this part denote or encode our unknown string. And then after action of all these gates, I have to repeat action of these operators. This is Adamar gates, and measure the states of fast qubits. No, we do not interested in the measurement of the last one qubit. So the unknown string is encoded here because we have action of controlled NOT gates on the qubit 1 and qubit 2, qubit 0 and qubit 2. So these qubits, qubit 0, qubit 1, control this action, which can be done, which can be achieved in the state, for the state of qubit 2. This is not the second. It's a previous. Okay, thank you. So if I would like to encode string 0, 1, I have to use this protocol. So the first protocol, you can see in this first protocol, you have just action of controlled NOT gate on the state qubit 1 and qubit 2. The pointer is open. But okay, I will explain by myself, not with this pointer. In this case, you have unknown, in the second case, you have unknown string 1, 0. Okay. You have unknown string 1, 0. And you have action of controlled NOT gate on the qubit 1. And if unknown string is 0, 0, we have actions of this controlled NOT gates on all these qubits. So if we see in our unknown string 1, the number 1, to encode, to create the quantum oracle corresponding to this string, we have to use controlled NOT gate, which acts on the position of qubit in this string. So the first 2 qubits encode these positions, these numbers. Qubit 0 encodes the first number, qubit 1 encodes the second one. So in this case, I have 1, 0. So I have 2-qubit gate, which acts on the qubit 0 and qubit 2. And I have 1, 1. So I have twice. I have to act with controlled NOT gates twice. And also the questions for students. So what do we have in this case? What unknown string is encoded with this oracle? So we have action of 2-qubit gates controlled NOT, and this gates acts on qubit 0, qubit 1, and qubit 3. Because that's why we have the following string here. Okay, maybe there are some questions. What's this?
So we have qubit 1. One, 1.
Yes, because we have ones, therefore we have all these control NOT gates that acts here on this position.
Then
0, therefore we have missed this action, so qubit 2 is not controlled. And 1. This is the simple rule how to create quantum oracle for this algorithm. And what is the result of this programming? I have a notebook prepared for this algorithm. So after performing this quantum protocol, here we have quantum measurement of states qubit 0 and qubit 1. And according to the rules of quantum mechanics, principle of measurement in quantum mechanics, we obtain, if you measure in standard basis, so you can see here the letter. So we measure in basis zeros and ones, the basis states of sigma z operator. And if we have standard measurement in standard basis, in other words, we obtain with probabilities depending on the state we prepared here. We obtain probability with different probabilities. Basis states 0, 0, 1, 0, 0, 1, 1, 1. But if we construct this quantum protocol, we prepare here this state corresponding to this unknown string. So this state is just equal in ideal case to this state 1, 1. Therefore, even if we measure one time, if we measure one time, just one shot, we use just one shot, we obtain the answer on our question. What do we have? What string do we have? This is fascinating because we can achieve with the help just of one measurement, we can find answer on the result. What is our secret string? And the last theoretical part of my presentation is devoted. Yes.
We are talking about secret string and so on.
Yes.
Where it is.
Okay, so with students, we can encode with these zeros and ones different classical information. So we can two types of information we can use. So for instance, for zeros we have some case, and for ones we have another case of some variance, and we have combination. So for instance, this is theoretical algorithm which is presented and developed. First of all, this was developed as with Deutsch-Josa algorithm for finding the types of functions. Is the function balanced or is the function constant? And Bernstein-Vazirani presented another view on this problem. So how to find a secret string? So this string can also encode in function. So we can rewrite function in the following way. So function of some number with some variables is, for instance, this string. multiplied by this vector. So this components of S can be zeros, ones, and we have definition of function with the help of this unknown string, for instance. So this is used in mathematics as a theoretical problem. So how to find this function, how to find this signal, for instance. So I didn't look in details on the practical usage of just this algorithm, but these are like fast algorithms. Berstein Bazirani, not fast, Deutsche JOS is the fast algorithm, one of the fast algorithms that promise that we can achieve quantum supremacy. Because with the help of classical computing, we have to check each number. So we have to compute the number of computations depends on the number of elements in this string.
Like test.
Test for quantum supremacy, yes. Test for quantum supremacy. So this is very interesting to find not just practical problems, how to solve them with quantum programming, but also theoretical problems, fundamental problems, problems from mathematics, have to achieve quantum supremacy. Because the next step, it can be how to apply this in practice. So this is the answer. Are there other questions? Maybe
Maybe it's
5?
when
When?
We are shifted for the minutes. So
We started everyone.
then
we including discussion to meetings.
So, okay. Okay, so thank you, because on the answer, I will find the best way to show the last part of the presentation, and I also would like to show the programming. So with my PhD students, I study different, sorry, this may be because of PowerPoint, this shift is obtained of this plot. So I study graphs and I study networks with the help of quantum programming. And I consider quantum graph states, which can be constructed with action of 2-qubit gates. And we studied the entailment of these states and also have to find structural properties of these graphs with quantum programming. For instance, with my PhD student, Natalia Sosulovska, we considered quantum graph states constructed with controlled phase gates and found the entailment, and we calculate this entailment with quantum computer, with the help of quantum computer, with the help of real devices. I also consider quantum machine learning models. For this, I considered variational quantum states. What do I mean that I say variational quantum states? Now I hope you have clear understanding what do we have here. This is rotational gates. This is RZZ gates. So we have first block of gates and we have second block of gates. And we repeat these blocks with different parameters. The parameters I have here, and depending on the parameters, we can prepare different quantum states. They can be multi-qubit quantum states, not just 5-qubit quantum states. They can be n-qubit quantum states. And in general case of quantum state constructed with this quantum protocol, so for arbitrary number of qubits, for arbitrary parameters here, we obtained with our students this Roman Hredil, Valeria Pinchuk, Maria Sanyak, Yulia Shevchuk. All of them are our students. So we obtain the result for the entailment. Also, we calculate correlators, and we done this with the help of analytical calculations. So by hand, but also with the help of quantum computing. And the results of quantum computing are presented with dots, and the theoretical results you can see from this slide. So this is the recent paper, so you can see the details published on arXiv. But what is the reason of all these studies, and why do we need all these things? First of all, the fundamental properties, because to know how the entanglement depends, for instance, entanglement or other properties of quantum state depends on these parameters, is a problem. So theoretical problem. If you have expression, if you obtain general expression for arbitrary case, we can, in this case, knowing this expression, we can prepare quantum states considering particular cases of parameters. We can prepare quantum states, particular quantum states with particular entanglement. So this is important in quantum information. This variational quantum protocol is used in quantum machine learning models. So we can also, with the help of these results, we can achieve some improvements of quantum machine learning, but this will be in the next steps of our studies. And now I would like to show some programs, because just theoretical presentation is very nice, but I prepared material for students, and may I okay, you can share here. Just this in private window. You can see there, but not here.
Seems to basically in the middle.
Maybe there are some questions. We have time for technical solutions.
There was some plot.
So the entanglement, this is the main difference between classical and quantum computation. Yes.
What is the main difference? Entanglement and superposition.
Yeah, it's more easily realized in quantum computing.
In the case of 1,000 qubits, you have superposition of 2 to 1,000 number. So this is huge number.
But another question, so in quantum computing, this is gates, this works with some probability. So it's not 0, 1.
Okay.
So it seems for such micro, very small physical systems, so the errors not probable than in classical computer, which
Yes, you are right. You are right. You are completely right. So we have not achieved quantum supremacy in huge number of problems because of the quantum errors. Each gate acts with some error. For instance, NOT gate acts with error 10 to minus 3 order. Controlled NOT gates act with error 10 to minus 2, sorry. So if we have quantum protocol and we have combinations of different 1 qubit, 2 qubit gates, we have the sum of these errors. So we cannot, that's why we can't simulate complex model just now on the real quantum devices, because of the quantum errors, we obtain just noise, not the results, but the noise. Also, the measurement has error. So we have errors of measurement, quantum measurement. So each step is not clear and it's not exact. But even in such case, the supremacy achieved in few problems, but it's very important also to find theoretical knowledge how to achieve this supremacy in future. But also another problem is how to achieve supremacy, quantum supremacy, or how to compute something in real quantum devices. So how to create the algorithms which are stable and which are resistant to these errors. This is the problem. So we have a lot of things to do right now, even in the case of quantum technologies of this level of evolution. But they are fascinating. As for me, 2 years ago, I programmed on quantum computers 5, 7, 12 qubit protocols, but currently we have a possibility to program on more than 100 quantum computers, which are opened due to IBM platforms and others. So the largest quantum processor is 1121 qubit, produced by IBM. So this is fascinating number. 2 to the 1000 is fascinating number. So, oh, nice. Thank you. So I prepared this notebook. So we use Qiskit. This is a prepared framework for programming with quantum devices, also quantum simulators in the frame of Python. So I run this first. Maybe I will just show to because I did all this manipulations, and you can see all these protocols here. So how to create a quantum protocol with the help of quantum programming, but not with the help of quantum composer or these quantum protocols, but with usage of Python. So we create quantum circuit. This is, you can see, this is quantum circuit which contains 1 qubit, this first number, and 1 classical bit to write the information from quantum measurement. Then we act with X gate. X, it is not gate in quantum programming, on the qubit 0. Then we act with H gate. H is Hadamard gate, the qubit 0. And we measure the qubit 0 and write the information from measurement on the classical bit 0. Then we can present this quantum protocol. So we act with X gate is not gate, Hadamard gate, and we measure. And we can run this quantum protocol. In this case, I used RS simulator, which is classical simulator of quantum computing, produced by IBM. And I ask, execute my quantum circuit, and I put here the number of shots, 1024. Why do I use this huge number? Because I would like to achieve not huge statistical error. So depending on this number, the statistical error is proportional to 1 over square root of this number. And then after the measurement, I obtained the following. I obtained the following results. So I obtained that 545 times I obtain that the state of qubit is 1. And 479 times, I obtain that the state of qubit is 0. So this is statistics of our results, and we can plot them. So I have counts, number of counts, and I obtain zeros and ones. Then I can apply here different 1-qubit gates, single qubit gates. It's sigma x, sigma y, sigma z, rotational gates, phase gates, and all these gates acts with different parameters on the state of qubit 0. So the second parameter is here. And I can represent this program with this quantum protocol. And also I can use different I can prepare different states with the help of 2-qubit gates. So you know already controlled mode gate, slope gate, and measure. Here I measure the state of qubit 0 on the classical bit 0, and measure state of qubit 1 on the classical bit 1. And after this, I achieve the following result. So I have visualization of all these gates. So it's more convenient, of course, in the case of multi-qubit quantum programming to use this representation. And the results of quantum programming is the following. So we have number of shots is equal to 1024, and when 255 times we achieve that the state of qubits is 0, 0. Another result was 0, 1, 1, 0, and 1, 1. So we have histogram corresponding to the results of measurements. And on the basis of this data, we can calculate the properties, or we can find the answer. For instance, we can study this spin in magnetic field. So we can prepare here the operator of evolution corresponding to the spin in magnetic field. And this is quantum protocol for these studies. We can consider Eisen model. So Eisen model means that we have two spins with interaction sigma z, sigma z. And this operator corresponds to this operator of evolution. And the initial state is prepared as superposition of all the basis states. Not 0, 0, because it is an eigenstate of this operator of evolution. Another representation of this Eisen model. So this gate was represented by IBM very recently. But if you do not have possibility to program RZZ gate, you can represent this gate with controlled NOT and RZ gates. So we consider different representations for qubits and for gates in quantum programming. Two spins with Heisenberg model. So if we have two spins with Heisenberg model, we have ZZ term, XX term, and YY term, and we can program this. And the last one for today is this Bechstein-Mazerani algorithm. But for string 1, 0, 1, 0, and we measure 4 times. So we measure 4 qubits, 4 fast qubits. And what do we achieve as the result? Just the string, which is secret. So we have number of counts equal, which equals the number of shots, because we have prepared just one basis state corresponding to the secret string. This may be the end. Thank you for your attention.
Thank you, Khrystyna. Now questions, comments? Everything clear?
What most interesting problem that was solved?
as for me, the most interesting and most fundamental problem that can be solved with quantum programming is solving of Schrödinger equation. So finding the eigenstates and eigenvalues of Hamiltonians. And it is the most general case of spin systems with Eisen model. Because why Eisen? Because the operators commute. In other case, we have to use trotterization procedure or have some kind of manipulate with this Hamiltonian, with this exponent, and to represent them from my side.
Yeah.
But also, I'm theoretical physicist. But if I, from the point of view of practical problems, so I have to say that students like, and I like, quantum teleportation, which can be realized with quantum programming. But this is not the same as in the core idea of quantum teleportation is to teleport state from one particle to another particle, but this particle had to be in huge distance. So this is what we teleport the state from one qubit to another qubit. So we perform swap operator, but we consider this quantum protocol for teleportation. But this is for students. For me, as also from practical point of view, I see that a very interesting direction of quantum programming is solving of the optimization problems. Because with students 4 years ago, 2022, it's 4 years ago, we solved just model problem, but this was problem of finding the optimal position for sensor position of the optimization for BMW challenge for driving without pilot on vehicles. So we tried to find the Hamiltonian, which describes the systems of sensors and the different types, positions of the sensors, the locations on the vehicle, and all the constants in Hamiltonian, in this case, contain information about the efficiency of this position. So we had data from BMW, so it was challenged, and we solved a model problem and proposed the solution of this problem with quantum programming. So the optimization is nice direction in quantum computing.
Is there any